Hi everyone, my name is Nassar and I will now present our work LAVA, Label Efficient Visual Learning and Adaptation. LAVA is a method for visual transfer learning with limited labels. It achieves state-of-the-art performance on multiple semi-supervised and few-shot image classification benchmarks. In low-shot transfer learning, we first pre-train an initial model on a fully labeled source dataset. Then the goal is to adapt this model to a target dataset with only few labeled images. We consider a general setting where the target classes and target visual domain can both be different from those of the source. A commonly used transfer learning method is to simply train a model in a fully supervised manner on the source dataset, then fine-tune the model on the target dataset. However, models trained with supervised labels only encode information needed to discriminate trained classes and discard any other information even if it's useful for the transfer task. This leads to the so-called supervision collapse. To illustrate, consider the source dataset includes person and chair classes. When transferring to a novel class such as curtain, a supervised model focuses on irrelevant representations and ignores the content that actually matters. In LAVA, we highlight and address two different types of the supervision collapse. The first is what we call class collapse, and it happens when the model confuses a target class with a source class when they share superficial similarity. For example, here the supervised model retrieves these book images as the nearest neighbors to the Mona Lisa target query image, instead of retrieving the correct Mona Lisa class images. The second type of collapse is the domain collapse. Here, the supervised model retrieves relevant images of a cheeseburger, however, in the natural image domain instead of a clip art domain. To overcome supervision collapse, the first ingredient of LAVA is to employ self-supervised learning. We use the recently proposed Dino self-supervised method to train our initial source model. At transfer time, we fine-tune the initial model on the target images without using any labels. The rationale is that self-supervised representations are learned in a task-agnostic manner and hence encode information beyond just classes, leading to better generalization ability. LAVA's second ingredient is using weak language supervision to enable low-shot transfer and avoid class collapse. After training the source model, LAVA learns a language mapping between visual image representations and the class label embeddings obtained via a pre-trained language model. At transfer time, this shared vision language space enables efficient adaptation to target classes by exploiting their semantic similarity to source classes. Finally, LAVA leverages unlabeled target data by employing a novel pseudo-labeling strategy based on multi-crop augmentations. For a given unlabeled image, LAVA obtains pseudo-labels by averaging teacher model predictions over multiple resolution crops of the image. Using multi-crops improves the pseudo-label quality as it accounts for image local and global features. We first evaluate LAVA in the semi-supervised image classification setting. On ImageNet, LAVA improves over state-of-the-art by up to 1.2% when only 1 and 10% of the labels are used. When transferring from ImageNet to DomainNet, LAVA is consistently better than the baselines, with more pronounced gains in the low label regime. The results also suggest the important role of self-supervised learning when the target domain is different from the source. We also evaluate LAVA in cross-domain few-shot transfer on the challenging Meta-dataset benchmark. LAVA shows strong performance where it outperforms state-of-the-art on 7 out of its 10 datasets.